Hey, Tyler. Okay. Hey, everybody. I'm sorry.
Good afternoon.
Okay, sorry. I had two instances going. I'm having issues with my Zoom and like my single sign-on for my company Zoom conflicts with my City at U Zoom, and so it won't let me like log on. It's weird. I'm trying to make it so it doesn't require me to start the meeting, but it didn't work. So sorry about that. Okay. I helped some of you with the homework, and then some of you turned it in on your own. So great job. Thank you guys for reaching out to me, those of you that needed help to get it done. This week should be a lot simpler, but my plan this week, since we're only covering one chapter, it should free up some time. We'll go a little slower. The examples they're mostly just like simple calculation type things and working through different types of problems related to probability. So we'll go through them a little bit slower, and then we'll kind of go over how you can approach the homework that's due on Sunday. So if you haven't started it, that's okay. If you have started it, you can kind of follow along. So we'll do that at the very end after we have our class discussion about predictive analytics. And that way, maybe it'll give you a little bit of a head start. And then again, I'm happy to meet. If you guys want, I can actually set up like a standing meeting on like Saturday or Sunday morning and just call it like homework help or something and kind of make myself available consistently to answer questions. So, or we could just play it by ear depending on who needs help and when, but I just wanted to throw that out there. So, okay. And here we go. Let me share my screen. Okay, so can everyone see my screen?
Yes.
Perfect. Okay, so today we're covering probability, and that's it. Oh my gosh, I was gonna make a note, and now I don't know what I was doing. Okay, sorry. Okay, so we're covering, oh, I was gonna take attendance really quick. This is my first time teaching lectures, so I'm still getting into a rhythm here. We're going to talk about the first half of the chapter, take a break, go over the normal and binomial distributions. We'll talk a little bit about Poisson and exponential, but not really in depth, just kind of what they're used for. None of your homework doesn't cover that stuff. And then we'll talk about predictive analytics. Hopefully you guys have had some time to do the reading and look at the articles. I think they're really interesting, and I'm excited for that discussion. And then at the end, we can answer questions and kind of go through the assignment that's due on Sunday. Okay, so when we are dealing with business problems, we have to deal with uncertainty. And we can calculate uncertainty at some level, or we can quantify it at least. And so whenever we have a method and we're modeling something, there's always a caveat that assumes there's some level of error that we don't know for sure. So in the language of probability, we would call any variable that has uncertainty tied to it a random variable. And each random variable would have an associated probability distribution. And it would list all the possible values of that random variable and their corresponding probabilities. So it sounds like a lot, but as we go through the examples, you'll see what that kind of means in terms of a concept. So the book provides this like workflow for assessing uncertainty and for dealing with it. And I just want you to focus on the key part of this, the main steps. So we're looking, they give you all this extra information. Like the first part is which inputs are important for the model, and then which of those do we know are certain, and which of those are uncertain, which of those are random variables. They talk about if you have a lot of historical data, you could use a program like @RISK, which is in the Palisade tools, suite of tools that you guys got. We're not going to cover it in class, but if you're feeling super ambitious later on in future chapters, you can look at how they use @RISK. I actually use @RISK when I build cost models for the government. So all that means is if I'm building a $1.5 billion cost estimate, each component of that estimate, like software engineering, has some uncertainty to it. And so there's uncertainty around the amount of hours of software engineering I'm estimating, which might be plus or minus 15%, or there might be minus 5% to plus 20% if I really am not sure. And then there's also uncertainty or risk around the labor rate, because I'm approximating a labor rate based on data, but it's possible when we go to award the contract, the rate might be higher, could be a little lower. It's however that plays out. So a tool like @RISK goes in and it looks at all these variables for each, or all of the risk for each variable, and you tell it what distribution you want to use. In my line of work, we use triangular, which is actually simpler than using a normal distribution, and it does all the math. So that's all that is. So then we got to model the problem. We can use Excel formulas, business logic, whatever model we're building, we would construct it. We'd look at the outputs, and then we provide information about that uncertainty. So the mean and the standard deviation, we're saying how much variance is there around our estimate. And then you make decisions with that information. So that's what I want you guys to focus on. This other stuff is just kind of extra information. You'll hear sometimes people talk about uncertainty and risk. Uncertainty is random. We can't control it. It just is there. Risk, it depends on your position, and risk can actually be positive, which we would call an opportunity, or negative, which means it has like a cost impact, or some impact that's bad. And just be aware that they're different terms. You can mitigate risk usually. You can come up with ways to get around it or lessen it. You can't mitigate uncertainty. Okay, so here we go. Probability. All right, so a probability is a number between 0 and 1 that measures the likelihood that something's going to occur. So if the probability is zero, it can't occur at all, and if it's 1, it's happening. And if it's in between 0 and 1, then that's telling you exactly how likely. So if it's like 0.1, that's not very likely. That corresponds to, like, if you want to think about it in terms of percentages, that would be like a 10% chance that something occurs. If it's 0.9, that's a 90% chance. So that's the more you move toward 1 or 100%, the closer that event is likely to occur. And for our sake, you'll see the probabilities listed either as percentages or as decimals. We don't talk in terms of odds, just more work to do in our heads. So the very first basic rule of probability is of complements. And all this means is if the probability of something happening is A hat or A bar, sorry, then the complement of that is 1 minus that. So if the A or not A. So if the probability of A happening is 40% or 0.4, the probability of not A happening is 1 minus 0.4 or 0.6. That's all that is. An event has to either happen or not happen, and the sum of those probabilities, the probability it happens and the probability it doesn't happen, has to add up to 1. No Schrodinger's cat events here, okay? For addition, the addition rule of probability, we need to distinguish between mutually exclusive events and exhaustive events. So they're mutually exclusive if at most one of those events can occur. So if we have 5 events and event 3 happens, then 1, 2, 4, and 5 can't happen. Exhaustive means that one of the events must occur. And the addition rule of probability involves the probability that at least one of them will occur. So this assumes that the events are mutually exclusive. So if that's true, then we just sum up the individual probabilities for all of those events. So if I have 5 events and they all have a 10% probability of occurring, and they're mutually exclusive, meaning just one of them has to occur, then the probability that any one of those 5 occur is 10 plus 10 plus 10 plus 10 plus 10%, or 50%. So that's all the addition rule is saying. Okay, so now we get into conditional probability. And this is where the notation might get a little confusing. So I've broken this out for you guys a little bit into like a word example to follow along with the book, and then also just to help kind of see like how to translate the mathematical language here into like a real life problem. Sorry, I see there's a chat. Oh, okay. Okay, so if we have 2 events, A and B, and B occurs and it changes the probability of A, then we say A is conditional. That probability is the probability of A given B. So that's what this this notation here, that's how it's read. The probability of A given B. So B happens, the probability of A changes. And then that's what this means. Okay, so we can find this if we know the probability of A and B occurring together, and then the probability of B individually. You can rework this formula. So if you have 2 out of those 3 pieces of information, you can calculate the other one. And so, for example, if we know the probability of B and the probability of A given B, we can actually find the probability of A and B both occurring by multiplying both sides by probability of B. We'd get, sorry for my really bad, this formula. And that actually is right here. So that's all I did was multiply both sides by the probability of B. So you can rework that formula any which way, depending on which 2 factors you have. And so let's apply this to like a real life example instead of talking in sort of A and B terms. So we have a company called Bender, and it has an end of July deadline. And they estimate, so they have 2 things going on. They need to get materials on time, and then they need to meet their deadline. So A is the event where they meet their end of July deadline. B is that they get the materials they need from their supplier by the middle of July. So they know the chances of getting their materials on time are 2 out of 3. So that's the probability of B. And then if they get the materials on time, they can meet the deadline. They estimate that probability of being 75% or 3/4. So that's the probability of A given B. So in other words, the probability of getting the materials is 2/3. The probability of meeting the deadline given they get the materials on time is 3/4. So we had that formula from before. If the probability of A given B is equal to the probability of A and B occurring divided by the probability of B. We don't know this. We don't know what the chances are that they will both get the materials on time and meet the deadline. So to figure that out, we could plug our values that we do know into this formula. So this is the probability of A given B. And then this is the probability of B. So if we multiply 0.75 by 0.66, we'll get the probability of A and B occurring together, which is 0.5. So there's a 50% chance that both the materials will arrive on time and they will meet their deadline. So if you're confronted with a word problem that's similar or that has conditional probabilities, I highly recommend that you write out the formula and then write out your probabilities in explicit terms, and then it's just plugging things in. So the book also goes through this decision tree, and I want to go through it just because I think it's useful to highlight the complements. So they gave us the probability of B as 2/3. And if you remember, that's a probability of getting the materials on time. So that means the probability of B bar, or not getting the materials on time, has to be 1 minus 2/3 or 1/3. So that's the complement rule right here. These things, they either get the materials or they don't. They have to add up to 1. I really need like a better tool than a mouse. So from there, we also know the probability of A given B is 3/4. So the probability of not meeting the deadline given the materials is 1 minus this, or 1/4. So from here, you can do some more math. So the probability of A and B, that was the 3/4 times 2/3. Now we can find the probability that they don't meet the deadline given the materials. And that's 1/4 times 2/3, because this is our value here, times B. If we go down the decision tree the other way, so the probability that they don't get the materials on time was 1/3. So the probability that they meet the deadline given that they don't get the materials on time is 1/5. And the probability that neither of those things occur is 4/5. And then they did the same. So they just calculated out the like all the various iterations. But I just wanted you guys to see for each node, everything adds up to 1. Okay, so this is just reiterating a little bit of what we talked about before. But if we're in a situation now where the probabilities are equal, then they're probabilistic independent events. So that just simplifies our formula a little bit. So the probability of A and B would be the probability of A times the probability of B. You would be told in it whether or not you were dealing with that situation. I don't believe any of our, I don't think we get into that level of detail. So what is an equally likely event? The most common reference people might think of first is like flipping a coin or throwing dice. In business situations, an equally likely event usually doesn't occur. And then finally, the difference between an objective probability and a subjective probability. So objective probabilities are estimated from long run proportions. So you run a trial a bunch of times and you use that data to calculate the relative frequency of events from within those trials. So it's measured. In business situations, sometimes, like for the example we just went through, the company was estimating based on like their expertise that they were going to get the materials on time. They estimated that probability. It is sort of based in data, but it's not measured by like 10,000 trials. It's just based on what the supplier has told them, what they've gotten in the past, what their experts know about those deliveries. So that's a subjective probability. That's an assessment that somebody made about the likelihood that that event would occur. So let's go through the example. Okay, so there's a couple things about Excel that we're going to talk about in this chapter, and a lot of it is just related to different formulas. The book talks a lot about calculating standard deviation and variance, and then they do it manually. I don't have any desire for you guys to know how to do those things manually when there's a perfectly good standard deviation formula in Excel. The reason they do them manually is because they want you to help understand the formula. So you're free to go through those examples and look at how they do the calculations and how they relate back to those formulas. But like I said, we're not like going to do any derivations or anything, and I'm not going to ask you to calculate stuff like that by hand. So I'm skipping over a little bit of that. But what I did want to show you is, so there's a couple things going on here in this simulation. They wanted to create some random data so that they could use the standard deviation formula. And so this is a cool function. You won't need it for homework or anything. I just want you to know it's out there. It's the rand function, which is random. If you input it like this and you don't give it an input, it will pick randomly a number between 0 and 1. So it'll generate like a random probability, basically. And so that's what they did here. They just created some fake data. Well, they created a lot of fake data, actually. Control Shift down. Looks like 400 different rows of data. And then they have this table here. So to create this fake data, they said anything between 0 and 0.12, pretend it has a market return of 23%. In the next bracket, 18. So if it falls between 0.12 and 0.52, if it's between 0.52 and 0.7, give it 15%. And then anything above 0.92 to 1 gets a return of 3%. And then over here, they use that handy VLOOKUP formula that we've talked about before. So this formula takes several arguments. The lookup value is this random, the number probability that we generated before. So it's looking at in this case, 0.903. And then the second argument is the table array. The table that we're looking up the value is right here. So we would select the whole table. Then we're gonna make that reference fixed on those cells by using the dollar signs, so that when we pull this formula down, our reference to that table remains the same. Another thing you could do is you could name this range. Anything you want. And just so you know, it recalculates probabilities every time you change a cell, that random function. So the numbers are going to keep changing because I have automatic calculations on. If you ever want to prevent that, you can I think there's a way to set like a seed, but I'm not going to do it right now. So I have this lookup table. Instead of doing the hard reference like this, I could now use the named range. And then which column is what am I pulling from the reference? So if I'm looking at this number, the value I want returned is in column 2, because this is column 1 and this is column 2. So when I do that, they all changed again, cracks me up. So 0.34, so since it's not 0.52, but it's higher than 0.12, it pulls that 18%. So that's what the VLOOKUP is doing. So that's really all I wanted to show you from the spreadsheet. Then they just calculated, they used the average formula for that data to calculate the average return. And then they calculated the standard deviation. Notice they use the sample standard deviation. So there's the standard deviation .p, which is the population, and .s. Most of the time we'll be using sample calculations, not population calculations, because we rarely have the full population measured. Okay. Let's see how we're doing on time. Pretty good. Okay. Before we get into, well, actually, this is related to the normal distribution. So I'm going to stop here. Do you guys have any questions on what we've covered so far? Okay. I have a feeling that the next section is going to take a little bit longer. So I'm going to start it since we're kind of running ahead of schedule, and then we'll pause in the middle and take a break. Okay, so when we're dealing with random variables, we know they have uncertainty. We're trying to figure out what that uncertainty is. Discrete random variables have like a finite number of possible values, and continuous random variables have a continuum of possible values. So if you're counting something, that's usually a discrete distribution. If you're measuring, that's usually continuous. As we go through, those definitions will sink in a little bit more. Mathematically, the difference between those is that when you're dealing with a continuous probability distribution and you want to find probabilities, you have to use calculus to find the area under the curve, and it's like a whole thing. We're not going to do any of that, but that's kind of the key difference. So when we're dealing with a discrete random variable, things are a lot simpler. So if there's k possible values, because it's a finite number, they denote those each distinct event, x1, x2 through xk. And we'll talk about the probability of a specific event happening in one of two ways. You'll either see this notation, the probability that x equals x sub I, or the probability of x sub I. I believe generally my preference and the preference of the book is to use this notation right here. So if we have like 6 events, x1, x2, x3, x sub 4, x sub 5, x sub 6, the probability of x sub 3 would be right, or x, I guess we'll do 2 since it's right here. This is the probability of the second event, x sub 2. These probabilities cannot be negative. And then they have to sum to 1. Cumulative probabilities are not as simple. We talk about those in terms of like a variable being less than or equal to some particular value. You can't, if you are talking about a continuous, oh, sorry, we're still, okay, cumulative probability. So if you're talking about like, what's the probability that given 4 possible values for some variable x, each with 4 different corresponding probabilities, you want to find the probability that that value, the random variable, is less than or equal to some amount. You would just use the addition rule. So in this case, they have some random variable x that has 4 possible values. So this would be like x sub 1, x sub 2, x sub 3, so little x's, x sub 4. And each of these has a corresponding probability. So the probability that the random variable x is 10 is 15%. The probability that it's 20 is 25%, so on. So if we want to know what the cumulative probability is that x is going to be less than or equal to 30, that's inclusive of 30. So we just sum up the probabilities of x being 10, 20, or 30, and we get that. And if you do that, if you sum those up, you get 0.75. So that's the cumulative probability. The inverse of that would be the probability that x is greater than 30 or x is equal to 40, which is 25%, or 1 minus 0.75. Okay, this is important because it's going to come up in your homework. Don't let this notation scare you. If you want to find the mean of a weighted sum, it's a weighted sum of possible values. So the mean is also called the expected value. In your homework, it's going to ask you to calculate the expected value of something. So they're saying calculate the mean. So you're just going to use the formula for that. And all this is the value multiplied by the probability of that value. So if we go back here, we can calculate the mean for this, or the expected value of x. It would be 10, which is x sub 1, times the probability of x sub 1, which is 0.15, plus 20. And if anyone sees where I'm going with this and has a calculator handy, I actually didn't calculate this out. So, but it's basically a sum product. If we were in Excel, that's what we would use to do this. We would use the sum product formula. 0.35 plus 40 times 0.25. And that would give us some number. I don't have a calculator handy. That would be the mean, or the expected value. So that's all that notation is. This is x sub 1 times the probability of x sub 1. If you look at this slide, that's the same thing I just wrote, but where I goes from 1 to k. So in our case, I would go from 1 to 4. So, and this is the giant sum signal. So it's the sum of products. So sum up x1 probability of x1 plus x2 probability of x2 plus all the way through until you reach k. Okay. Pretty simple, straightforward calculation, despite the crazy looking notation. The other measure that we calculate is variance. The book really loves to go through this calculation by hand, but there's a variance formula in Excel, and that's what we're going to use. So variance is, this is the little, for a population is noted as sigma squared, and mean is often written as mu, or just variance of x. It's sum of the squared deviations of the possible values from the mean and the weights of the probability. So it's a slightly more complex formula. It's the x value for I minus the expected value of x, or the mean. Like so for example, if we were doing this in that last example, x sub 1 was 10. We didn't calculate e sub x because I don't have a calculator. Whatever that value was, you'd square it, and then you'd multiply it by, I think it was the probability of x sub I. I don't remember what this number was, but, and then again, it's a sum product. So that gives you a measurement that's in squared units, and mathematicians generally don't like squared units for measurement. So if you take the square root of that, you get the standard deviation. So that's all the standard deviation is. It's just a square, the square root of the variance. It gets rid of this little squared factor here. Okay, so let's just look at how some of these calculations go. Market returns. Okay, so I read this out because they're just going through by hand. So for this example, you can follow it along yourself, but I'm not going to go through it in class because you wouldn't do this in person, but they're showing you how those formulas look when you're talking about rows of data. So it might be good in your mind to kind of wrap around how the formula is working for variance and standard deviation, but they're doing it by hand in this scenario. So and you can always come back to this slide as well and look at the formulas that they're using to do it by hand. But I'm going to keep the focus on how you would calculate these things using the Excel formulas because they exist, and it would be kind of silly to not use them. Okay, so before we can do that, we have to talk about the normal distribution. The normal distribution in statistics is incredibly important, and it's going to be the most common thing that you run up against in future courses whenever you're doing analysis or looking at models and you're looking at data. It's that classic bell-shaped curve that you may have heard about in like stats lingo before. So when we have a normal distribution, the things that dictate what shape it takes is the mean, which tells you where on the curve, where on the x-axis the peak of the curve occurs, and then the spread. So, and that's the standard deviation. So a really tight curve has less a smaller standard deviation. A wide curve has a larger standard deviation, meaning the data is more spread out. So in other words, this is a nice way to look at it. So this is the mean. The mean is where this peak occurs. So if we change the mean, we're just changing where on the graph that peak occurs. If we change the standard deviation, we're flattening or kind of raising the curve. We're changing the density of the curve. So the black line is a smaller standard deviation than this. Whoa, I have no idea why I did that. Okay, well, anyway, this curve right here. If we want to, just so you know, we're going to talk about a standard normal curve. A standard normal curve, all that means is that our mean is centered on 0 and our standard deviation is 1. So it's just a way of having a nice clean curve. And there's a way to convert any distribution into a standard normal, and we'll talk about that later. Okay, so we had talked about discrete distributions. For continuous distributions, we don't have like a list of possible values like we did before, where we had like 4 possible values and they all had an assigned probability. Now there's a continuum, and when we look at this continuum, technically it goes on forever, but most of the likely values fall within this curve right here. And so if we can't actually find the probability of like an exact point on this curve because it's a continuous curve. So the probability is like infinitesimally small, basically 0. So when we need to calculate the probability with a continuum, we use what's called a density function. Don't get too wrapped up in this part of it, but it kind of looks like acts like a histogram. So if we're talking about the probability of some event being between 65 and 75, the way that we would calculate that is by measuring this area under this curve. And that's why they talked about needing calculus. And this is why we have Excel to do this for us. So we'll talk about the language to figure out, like if we want the probability that, let's pretend that's at 55, that the X is less than 55, we'd be measuring everything under here. Okay, so this is what we were just talking about. We have this kind of infinite distribution with a small area of interest. And the formulas for getting mean and standard deviation and our density function are a lot more complicated, and you don't need to know it. So I'm not even going to stress you out with that. But what I do want to cover really quick is the standard normal. So a standard normal deviation has the mean of 0 and a standard deviation of 1. And this is the notation for a normal distribution with a mean of 0 and a standard deviation of 1. So if you see this, it's a standard normal. If we want to standardize something, there's a formula for that. We just take each value of X, we subtract out the mean, and we divide by the standard deviation. So in our spreadsheet here, let's say we have some data on, looks like annual returns for 30 funds. So this data right here is not standardized. We can calculate the mean on it by using the average formula. If you remember, average is the formula for getting the mean in Excel. And then we're going to use the standard deviation formula for a sample for the same data set. So now we have our mean and standard deviation. If you remember, the formula to get the z value is the x data point minus the mean divided by the standard deviation. So what that would look like, take the x value, which is for this row is B8. And then they named our ranges, which is nice because they'll stay fixed. Subtract the mean, divide by standard deviation. So mean was named here and standard deviation. So when we do that for all of our values, we get, now we have a normal distribution. And if you look at the, so to make sure that worked, if you ever want to check, if we take the mean of this data, it's 0, which is what we want, and the standard deviation is 1. So we've now created a nice standard normal standard deviation. And the reason why this is handy is because we have some idea now of how many standard deviations above and below the mean our data is, and we can look at it at a glance, and right away we could spot any outliers. So like for example, where is it? This one right here is more than 2 standard deviations away from the mean. That's a high value. So we might look at this data point and see like why it's so high. It might be an outlier. If it's more than 3, then we definitely have an outlier. And we could even format this. You saw in last week's examples some conditional formatting, which we didn't touch on a lot in class. But if you come up here, you can set some rules. So let's see, I want to highlight anything greater than 2. And then I'm going to add another rule, anything less than -2. And it's just that one value that was kind of questionable. So that's why we normalize. It just gives us a quicker way of looking at the data. But okay, this is a good place to stop. So let's take a break. Oh, one thing you guys can happily ignore is this section about calculating your own tables. We're never going to do that. So we're going to pick back up with doing some normal calculations in Excel. So let's take a 10-minute break, come back at 2, and then we'll keep going. And unless anyone wants to stay here and ask me any questions. Okay, I'll see you guys at 2. Resume. Okay, so we're looking at our calculations in here. Let me see if I have a. Oh, were you guys not able to see my screen that whole time?
Thank you. I thought I was going crazy.
You could have spoken up. Sorry, I thought I was sharing. Okay, so I'm going to play around with my tools really quick. No, I was trying to show you this Excel spreadsheet, so I will fix that here in a second. I'm just looking for my little tool. Okay, so here's what we were calculating before. If we drew this standard distribution, remember the mean is at 0. Can you see what I'm drawing? I'm just curious if this is actually working.
Yes.
Cool. All right, and this is our x-axis. So we're looking for less than -2. So in this case, we'll say if -2 was like right here, that's easy. We're just doing this area. For greater than 1, we're calculating this area, but remember the formula is going to actually calculate everything but that area. So we do 1 minus the result. And then for the between values, draw a new distribution. So they said between what, negative 0.4, which is almost right at the top, and 1.6. So we want this area here. So if we do the probability of just 1.6, we're going to get the calculation for all of this. But we don't want all of this. And if we do the calculation for negative 0.4, we're going to get this area. So the entire amount subtract, and then we subtract out the tail on this end that we don't want, gives us the space in between. So that's just a way of visualizing it. I don't know if that's helpful. I think looking at the pictures helps me. So if you get stuck and you're trying to figure out like which rule to use, do you just use the calculation the way it is? Do you subtract it from 1? You can always draw it out if that helps you. And oh, here we go. Okay, and then see if that fixes things. So back to this. All I was pointing out was to get the probability in a standardized normal distribution. So it's the norm.s for less than -2. That's the simple formula. We just plug it in. Here's the parameter that it takes, and then the true argument. And then for greater than 1, we use the 1 minus. And for between, we use, we would subtract the 1 from the other to get that column of probability. Okay, for percentiles, so they want to know what is the 5th percentile of the standard normal. So the formulas that you'll use to calculate percentiles are the norm dot inverse, and it looks like this. We have the S in here because we're operating under the assumption that we're using the standard normal, where it's the 0 mean and the standard deviation of 1. So all you do is just plug in the probabilities when we're working with standard normal. So this returns the 5th, the 75th, and the 99th percentiles, the values that correspond. Okay, let's pretend we have a non-standard, because this is really what we're going to encounter most of the time. So now we need to know a couple of things. We need to, if we don't have a standard normal, that means that the mean is not 0 and the standard deviation is not 1. So we need to know what they are. So in this case, they're given to us. So we're working with a normal distribution where the mean is at 75 and the standard deviation is 8. So that might look um, 75, that's a fair, so, you know, or it might look kind of like that as opposed to our nice normal one over here. Okay, so now we're just using the normal formulas, normal distribution, but we need to put in a few more arguments. So it's wise to name your ranges, mean and standard deviation, so that you don't have to keep referencing those cells. You can just plug them in this way. So now we have to tell Excel for this function, I want the normal distribution, I want the probability of less than 70, where the mean is 75, the standard deviation is 8, and it's a cumulative function. So same rules. For greater than, we have to do 1 minus. And for between, we're subtracting 1 from the other. We just have these extra arguments that tell Excel. Whereas up here, it already knows, because you're telling it that it's standard, it already knows that those values are 0 and 1. So that's the key difference between those two formulas. For percentiles, same thing, just the 2 extra arguments. So the 5th percentile of this distribution, we would pull up the norm inverse function. The first argument's the 5th percentile, then the mean and the standard deviation. Okay, so let's look at why we might actually, like, why we care, I guess. Okay, so let's say we're looking at test scores to accept or reject applicants for a company. And we know that the scores are normally distributed and the mean is 525 and the standard deviation is 55. We want to calculate a couple of things. We want to calculate the percentage of applicants who are automatically accepted or rejected given the current cutoff rates, which are, so anything greater than 600 is a automatic accept. Anything less than 425 is an automatic reject. So we're calculating the probability of greater than 600 and the probability of less than 425. And then we want to find new cutoff values where we would only reject 10% and then accept 15%. If you're wondering, like, would I really ever do this? I'll tell you, I'm on the board of directors for an organization called ICEA, which is the International Cost Estimating and Analysis Association. And we have an exam that we administer so that you can get certified as a certified cost estimator analyst. And we recently moved our exam from paper format, where you had to have it proctored, to an online format. And then when we did that, we overhauled a bunch of the test questions. And so we know that we want about 70% of the applicants to pass. So we actually had to do similar calculations to look at our test data and our applicant data and figure out what those cutoff score rates would be to get to that ideal pass rate. So this is actually, like, not totally made up. You could really encounter these things in real life, and then you're like, oh my God, Google, I need to remember how to do it. But so in this example, they gave us the mean, they gave us the standard deviation. Again, we label these things so that our calculations will be easier. Okay, so the first question was about the current policy. They wanted us to figure out what percentage are accepted and rejected automatically given the current acceptance points. So we just document those points so that we have them. And then for greater than, remember, we need to do 1 minus. So to figure out the percent that are automatically accepted, we do 1 minus this automatic acceptance point. So that's the 600, everything greater than 600. The mean, which is there, the standard deviation, and true. And it's telling us that at the current points, about 8.63% are automatically accepted. For rejected, it's a less than, so we just plug in the normal distribution formula, give it our lower bound, the mean, the standard deviation. So about 3.45%. So they're asking, okay, we want to automatically accept 15% and we want to automatically reject the bottom 10. So at what point do we get to that automatic acceptance? What's that, where's that percentile? So to do this, The lower one is easy. That's just the normal inverse formula for 10%. And then we give it the mean and standard deviation. And it's saying test scores below 455 should automatically be rejected if you want the lower 10% to drop off. For greater than, for trying to find the greater than point, we have to do the 1 minus thing again, because we're subtracting out all this stuff to get the top 15%. So if you look at this formula, it's 1 minus the 15%. So we're actually trying to figure out the 85th percentile, if that makes sense. Like if you think about the curve, what value do we get to 85%? And then everything above that, we're gonna accept. And then the mean and standard deviation. So that's 582. So they currently are at 600 and 425. If they want to get to their new rates, they would set their new points to 582 and drop everybody that goes below 455. Any questions on this example? Hopefully it helps to start seeing how they might actually use these things.
No questions yet.
Okay. Thank you. Okay, so yeah, we're just gonna keep working through some stuff. It's just really helpful to see some real life examples. So in this one, let me just look up the backstory here so I don't get this wrong. What are we on? 5, 6. Okay. So we have, went too far. Quality control. We have a paper stock company that runs a manufacturing facility that produces some kind of paper product. And they have settings on their machines to manage the fiber content. So the fiber content is supposed to be 20 pounds per 1,000 square feet. So they say like this is basically like grocery bag fiber content. However, machines aren't perfect. There's random variations. So typically the fiber content varies according to a normal distribution. So the mean can be controlled on the machine, but the variability changes as the machine deteriorates over time. So they set the mean to 20. On a good machine, the standard deviation is 10%. As the machine wears down, it becomes 15%. So they've labeled these 3 ranges: mean, standard deviation of a bad machine, and standard deviation of a good machine. I don't know why they, oh, it's in alphabetical order, that's why. So 15% is the bad, 10% is the good, there's the mean. So this is all just background information from the story problem that we would document as we're going through. Okay, so if a roll of products fiber content is less than 19.8 pounds or greater than 20.3, we have to reject it. So we're already getting some language, less than and greater than. So we want to calculate the probability that a roll is rejected, both when we're on a good machine and when we're on a bad machine. And the point of this exercise is to kind of show you just how like small changes in standard deviation can really affect the other calculations that you do. So the other thing we did here is we documented our reject region. So we know our lower limit, we know our upper limit. It's good to write those things down and so that somebody who's doing this, who's reviewing this, can see all the factors. Okay, so for a good machine, the probability that it gets rejected, we want the area between 19.8 and 20.3. Those are all the things that we're going to keep. Or sorry, so we want the area below 19.8 and the area above 20.3. That's the probability of a reject. So we have to find two things here, which is why this formula looks kind of wild. So the probability of it being less than 19.8 is the simpler one. So we just plug that in, normal distribution, 19.8, the mean and the standard deviation, which were labeled, and we did, we're doing this for the good, so we use the standard deviation good. And then we also need to add in the probability of rejects for those greater than 20.3. So that's 1 minus the normal distribution for that 20.3 value. So the two of those combined will give us those outer bounds. So in other words, we're looking at, find my little handy tool. In this case, we have our distribution. Our mean is 20, and we have some, these are all getting rejected and these are all getting rejected. So we want to add this area and this area together. So this is the corresponds to this part of the formula, and then this area corresponds to this part of the formula. And then for the same thing for the bad, but instead of using the standard deviation of the good machines, we're just using the standard deviation of the bad machines. So now we have our probability of rejection. So look at the difference here. And on a good machine, the probability of rejection is 2.4%. On a bad machine, it's 11. So just that small change really affected the likelihood of a roll being rejected. And if I'm a company, that's a big deal. That's like a 5-fold increase in rejections. That's waste, and manufacturing waste is something that you really want to avoid. So that's pretty telling for, you know, just that little bit of difference in the standard deviation. So if you were a business analyst, this is where you would make your case for preventative maintenance on the machines and for better prediction of when a machine is starting to fail, so that you could correct it before you get to this high of a rejection rate. The other thing they do in this example is they wanted to see like the sensitivity. So they did a two-way data table where they took the on a good machine, they varied the mean and they varied the standard deviation anywhere from 10% up to 15%. So that kind of tells you, like, obviously a machine doesn't just go from good to bad. It starts to deteriorate over time. So if we look at what they did here is a two-way data table, which we've done before a couple times. You could try it on your own if you just wanted to make sure that you remember how to do it. But when you populate it, you get these values and you kind of get like a little bit of sensitivity. And just something to highlight. So if we set the machine to 20 as our thickness, our mean, it starts out with a rejection rate of about 2.4%. And then it goes up from there to 3.8 when the standard deviation climbs to 11%. When it climbs to 12%, we're now at like a 5% rejection rate. And so you can just kind of see this increase over time, all the way up to 11. So kind of interesting. I like their little mark here. When this illustrates the famous line that variability is the enemy. So those are things that we cannot control. All right. In this example, again, we're just practicing translating language into our formulas. So in this example, we have an investor's after-tax profit. And if any of you are finance people, this example makes much more sense to you. I'm like, okay, I understand the calculations, but the rest of it is probably why I'm not a millionaire. Okay, so Howard is investing $10,000 into a certain stock, and he estimates his annual return will have a mean of 5% and a standard deviation of 14%. His tax rate is 33%. This is all information given to us from the book, so it's not like you would be expected to know this. These are things you would be told. So if he makes a profit, he's going to pay 33% on it. If he loses money, he doesn't pay any taxes. We're going to calculate the probability that he owes $400 in taxes, and then the probability that he doesn't owe any money in taxes, meaning he doesn't make any money. And then we'll calculate the dollar amount so that his after-tax profit is 90% certain to be less than it says less than this amount. Oh, less than 400. Okay, so here's our inputs. 10,000, this were all given to us, his tax rate. They named these ranges. Remember, if you're naming ranges and you set up a spreadsheet like this and you know that you want your range names to match your labels over here, you can select both of them, come up to your name manager, create from selection, left column is where the names come from, and it would do it for you. That's just instead of doing them all individually. Okay, so the first couple things are pretty simple. We want the probability that he's going to pay at least $400 in taxes. So in this case, he's paying 400 or more, so greater than. So we need to do 1 minus. And the amount he's going to pay in taxes is going to be, so we need to pay $400 in taxes means he needs to invest more than that, because it'd be whatever amount he needs to invest and pay 33% on, and then that would equal 400. So they divided the 400 by the amount invested times the tax rate to get that information. And if you want to see, we can pull this out. Okay, 400. Okay. And then the mean and standard deviation come from the inputs we were given, and it's cumulative. So the probability that he's going to pay is like 30%. Pretty decent chance. If we want to look at the probability that he doesn't pay any taxes, so this would be not making any money, so 0. And yeah, so that's pretty straightforward. We're just, if he makes nothing or less than nothing, he pays no taxes. So anything less than 0 on our bell curve would be the right probability. So that's about 36%. So if we're looking at if we're thinking about what our curve looks like, okay, so he needs a 12% return. That's what I calculated before, to get to owe at least $400 in taxes. So the first calculation is everything over here. The other calculation is what if he makes 0 or negative? So everything over here. Okay, now we want to find the 90th percentile of the stock return. So for this one, we're just looking at this normal function here with for the stock return. So we're just asking it to find the 90th percentile with the mean of 5% and the standard deviation of 14%. And that's 22, almost 23%. But if we want to find the 90th percentile, like of the after tax, like after he's paid taxes, we would take the amount he's invested times this 90th percentile of his return times the tax rate, or 1 minus the tax rate, because that's basically what it keeps. So if you ever do like paycheck calculations, if you know you're paying 30% in taxes, you would multiply your paycheck by 1 minus 30 or 0.7 to get the 70% that you get to hang on to. So that's all that is. They're saying, okay, so his return is 10,000 times 23% or so. That's we're 90% likely. And then we got to take out the taxes. So he's only netting about 1,500. I don't know if that's good or not, but okay. Now we're going to move to binomial. All right. Binomial distributions are a special case where you're only looking at your sampling, where you have only 2 member parameters. So like they say males versus females. So 2 outcomes. So if we have like n independent trials, so let's say like coin flips, if the probability of success on each trial is p, so we'll say heads is p, then the probability of failure or tails is 1 minus p. So when we're working with binomial distributions, the calculations are similar to the normal, but just everything's a little bit simpler because we're working in this kind of binary world. So x is going to be the random number of successes in our N trials. And if that's the case, our binomial distribution has the parameters N, which is the number of trials, and P, which is the probability of successes. There's Excel functions for binomial distributions. So they work very much just like the normal calculations. It's just that it's a special case, basically, a simpler case. So if we're looking at, in the next example, we're looking at the number of successes in 100 trials of flashlight batteries. So a success means that after 8 hours, the battery is still functioning. There's a whole bunch of ways to use this. The key takeaway is that when you're working with binomial distributions, it doesn't show it. You have to reframe your events so that they fit the function, what it's asking. So if we have 100 trials, the probability of success is 0.6. They named their ranges N and P. So if we want exactly 58, then we call the binom distribution function. We tell it the first argument, we want exactly 58 successes. What's the probability of that given N trials and this probability of success of P? So that's calling 100 and 0.6. So the probability of getting exactly 58 successes is about 7.4%. If we want no more than 65 successes, now we're going to call we're going to okay, so that's inclusive of 65. We want no more than 65, so less than 66. So we'll call the binomial distribution. And notice the difference between these two. So when we want an exact number, we tell it false for this cumulative argument because we don't want the cumulative probability up to 58 successes. We just want that exact probability. So that's why it's false. In this case, we want to go up to 65, but we want the cumulative. So this is true. If we want less than 70, that's everything from 0 to 69. So we're going to put 69 as the parameter. If you put 70, you're including 70, and we want less than 70. So it's not less than or equal to, it's less than. So we need to use 69. So just be careful. And there's a note over here about this. So if you use true as your last argument, you're returning less than or equal to. So you need to reframe all of your problems into a less than or equal to unless they're equals. If they're equals, like this exactly 58 equals 58, you use false. But for everything else, we have to reframe the wording so that it's less than or equal to. So that's why less than 70 is less than or equal to 69. So we're putting 69 in this right here. So for at least 59, notice what they did. So if I were thinking about my distribution, I want to take 1 minus everything from 0 to 58, and that will give me every 59 and above. So that's why they call 1 minus and then 58, because 59 is included in that at least 59. On the other hand, if we say greater than 65, we're not including 65, so that's everything 66 and greater. So I want to subtract out everything from 1 to 65. So 1 minus, and then the distribution with 65. So I encourage you guys to like practice the reframing of these problems, but you need to always get them when they're cumulative to a less than or equals to, and then that will give you the argument here that you're plugging in to get the probabilities. To do between, the same thing, you would do the subtraction. Just note, so this is inclusive, so it includes 55 and it includes 65. So the first calculation, we include everything up to 65, and then we subtract out everything from 1 to 54, and that gives us 55 through 65. For this one, it's exactly 40. So that's an equals, that's easy. We just make sure that the n argument is false. And now we're looking at failures. So for failures, the probability of a failure is 1 minus p. So we're not looking at successes anymore. We're looking at failures. So instead of taking p in the argument, we do 1 minus p. That's the complement rule we talked about before. So if the probability of a success is 60, the probability of a failure is 40%, and that's what we want at that value in there. So same thing with these, just notice it's the n minus 1. And you guys can pull up these on your own too as well and follow along if you're trying to do these. I don't think you need to do these in the homework though. So and then they did some finding, so they did some trial and error, which is kind of silly. To find the inverse, you use if we're trying to find the percentile, the 95th percentile, we would use the binomial inverse formula, and then same arguments as before, NP, and then the percentile. And it says 68 trials. Or this, yeah, 68 is the 95th percentile. Okay. When we're working with binomial distributions, the mean and the standard deviation are a little bit simpler. The mean, or the expected value, is just the number of trials times the probability of success. So in our previous example, if you did 100 trials and your probability of success was 0.6, then the expected value is 60. So we expect 60% of those. That's how we got that to begin with. And then the standard deviation is the formula shown there. You don't need to do it by hand. It's just nice to know. The takeaway from this slide is just that in the real world, when we're sampling, we tend to sample without replacement. So like if you're doing a survey, each respondent is sampled one time and then they're struck from the list. If you were to sample with replacement, then it would mean that like it's possible that you could sample the same subject twice. So like I said, normally we sample without replacement, but the binomial model technically applies to sampling with replacement, but if you have a really large population and you're pulling a small percentage of it, you can safely use the binomial calculations because the likelihood that you like resampled and is very low. So that kind of mimics sampling without replacement safely. So if you do a lot of trials and you get a really large N, you start to get a normal distribution. That's all that the takeaway here is. It's just that you can see like the graph here is the cumulative probabilities of any particular value. And so for that reason, when you have a lot of trials, a very large N, and your probability isn't, your P isn't, probability of success isn't super small or super large, you can approximate with normal distribution. Okay, I think, yeah, to wrap up, we're just gonna walk through a couple more examples so you can see how these calculations are used. So this one's pretty simple. They gave us the probability of beating the market index in a year. So 37 weeks out of 52. So this would be our N, 52 weeks, and then the probability of success is here. So what are the odds that we did this well, had 37 successes in 52 weeks by chance? In our distribution, that would be 1 minus the binomial distribution of, because we want to know the probability of doing greater than or equal to 37 weeks. So there's our number, our total trials. And so we wanted 37 or greater, so they subtracted out 1. So we're calculating up to through 36. So just so you know. And then 52 trials. In this case, we're assuming, by chance, if you ever see like, what's the odds of doing it better by chance? That's 50-50. So 0.5 is our probability. And we are doing a cumulative calculation, not an exact calculation. So the probability of doing that well for one particular stock is pretty low. It's it's like 0.2%. However, there are 400 mutual funds, so the probability that at least one of those does that well is calculated a little bit differently. In this case, we just want to know, like, what are they're asking in this case, they want to know, like, what is the probability that just like at least one of them does that well out of 400. So now we want everything up to 0. Out of the 400 trials, how many of them would match this probability? And if we calculate that, there's actually a pretty good chance. So if you have one particular stock is not necessarily, like, the odds are pretty low, but if you have 400 mutual funds that you're looking at, the chances that one of them does that well are decent. And then they just created a two-way data table where they varied the amount of mutual funds that you have and how many weeks of beating the market. And I just wanted to see, like, does it help to have a larger amount of mutual funds, and by how much is it helpful? So you can see, like, the more funds you invest, the more likely it is that one of them is going to beat the market index 36 weeks in a row. And then you can see like 37, 38. So the more you try to push your luck beyond 36 weeks, the smaller your chances get, no matter how many mutual funds you have. Okay, in this one, we're looking at some information about the supermarket. And we have some amount spent per customer, and they told us the average amount was 85 with plus or minus $30 standard deviation. So the probability that a customer spends at least $100. So that's everything up to 100. But we want everything after that, so 100 or greater. So 1 minus the normal distribution of 100, given that mean and that standard deviation, the same formula we've been using for all these other examples. So there's the 31% chance that a customer is going to spend $85. If we have 500 customers, we can, what do they do here? Let me look at the, okay. So if we have 500 customers, then there's on average 154 of them will spend at least 100. So all they did is took the probability that any one customer spends $100 and multiply it by the total number of customers. To get the standard deviation, then they took the, they did it by hand. So they took the square root of the n times p times 1 minus p, which was that formula that we looked at in the slide before. You're not going to need to do that by hand, but just so that you understand what they are calculating. So they're looking at this sample of 500 customers, and they're trying to figure out the mean and the standard deviation. The new probability for at least 30% of those 500 spending 100 is kind of similar to the stock market example that we just did. We take the 30% times the number of customers. That's the amount that we're trying to get information. Minus 1 because we're doing at least. Then the number of customers, and is the trials, and the probability is that 31%. So about there's about a 68% chance that at least a third of those 500 customers will spend $100. Okay. So just note, I think in here, the key things to note with this example is that when we first calculated the probability for one customer, we were talking about the probability that any one customer spends at least 100. We're talking about a normal distribution. But then when we go into trials where they either do spend 100 or they don't, now we're working with the binomial distribution. And then this one's a little fun because it actually happens to us in real life. So this one, they're looking at airline overbooking. And if I'm an airline, and this airline analysts do this this type of analysis all the time because they want to maximize the number of seats filled in their plane, but they know that they're going to have some amount of people who don't show up to that flight. And so they oversell tickets, hoping that they fill as many seats as possible without overbooking. And the way they do that is, so if they have 200 seats and they have the probability of a no-show is 10%. We're going to start out by issuing, say, 215 tickets because we need to start somewhere. So the range names, so N tickets, and then P is the probability of a no-show. So we have these probabilities here. We want to know what's the probability that more than 205 show up. So in this case, we have a binomial situation because it's you either show or no show. So, and we're trying to figure out probability of successes. From funny. Probably, because I know Alaska's pretty good at this, but so we're looking at trials and failures. So we're using binomial. And we want to know what are the chances that more than 205 show up. So 1 minus binomial, we're trying to figure out probability of greater than 205, hence the 1 minus. Since it's more than, we're including 205 in that calculation, so we don't need to subtract 1. N tickets, that's our number of tickets issued, so 215. And we're trying to figure out like people who actually show up. So we have the probability of a no-show. So we want the probability of a show, which is 1 minus that, which is 90%. And this is cumulative. So that probability is pretty small. If we issue 215 tickets, the odds that more than 205 of those people will show up is like 0.1%. Okay. We're going to do the same calculation, the same formula, just with a couple different numbers. So we're going to do it for 200. So if I issued 215 tickets, the odds that more than 200 show up is 5%. So that means I'm issuing probably there's a 5% chance I'm issuing a refund and some apology money. For 95, the chances are really good, 42%, and then at least 190. So if I'm an airline, now I'm playing this game. I want to figure out how many tickets I can issue and get 195 seats filled. I don't want to push my luck and try to get all 200 filled because when I'm looking at my probabilities, you know, I'm kind of looking for that range in between 195 to 200 so that I'm not, because it is expensive for airlines when they overbook. So we're trying to avoid that. So what they did here is they did a two-way data table and they varied the amount of people showing up, these probabilities here with the number of tickets issued. So if we change the amount issued, the probabilities change accordingly. If we issue fewer tickets, it's less likely that we're going to have more than 200 or more than 205 people show up, but my plane only seats 200. So we kind of have a problem at this point. So somewhere in here is the sweet spot for an airline. And it's gonna, like, if you look, you're kind of figuring out like how much risk as an airline do we want to take. So some airlines may take more than others. But if I do 218 tickets issued, there's a pretty good chance, that most of my seats are filled. But there's also a pretty high chance that more than 200 people are going to show up. 16% is not necessarily a risk that I want to take. And then the probability that more than 5 extra people show up is pretty low, but still 1.3. So I could be issuing anywhere from like 3 to 6 vouchers. I may not want to do that. So if I do 215 tickets, I reduce my risk here down to like 5%, and almost definitely not going to have to issue more than a few vouchers. But look at my chances of having my plane be nearly full. They're pretty low. Pretty good that, but I could have quite a few vacancies. So these kinds of analysis can help make these kinds of decisions. If it were me, this would be the first step. The second step would be figuring out how much do those vouchers cost and how much revenue are you making? And so you got to decide, like, is it worth the, like, at what point are you losing money by issuing too many vouchers, basically. So this is probably about the sweet spot. Maybe somewhere between 218 and 221 tickets for a 200 seat plane based on this data. Okay, and then finally, the point of this spreadsheet, and I'm going to let you guys walk through it on your own in the book. It's to show you why probability allows for stations to call an election when they only have like a small amount of data in. And this is a gross oversimplification, but it kind of just shows you like how the probabilities change so quickly when you're dealing with these types of distributions. So I'll let you guys go through that on your own. I really want to get to our discussion. So the last 2 things we're going to talk about are just for your information. You'll hear Poisson a lot as you go through future courses in analytics, because it's very common in queuing theory and like arrival, anything that has like an arrival rate or that type of distribution. So Poisson distributions are discrete, and they're just a different type of distribution. They have different calculations for mean and variance, and they have one parameter, which is lambda, and it has to be positive, and lambda is just the arrival rate. That's the only parameter of a Poisson distribution. All Poisson distributions increase and then decrease. So they look like a skewed normal, basically. And the lambda just changes how quickly they increase and decrease. So if I'm a bank manager and I'm trying to figure out customer arrivals and I want to model the arrivals in an hour to figure out like how many tellers I need to keep my queuing time down. I don't want my customers to wait more than 5 minutes. Let's say I want to model those arrivals. I could use a Poisson distribution and then do a bunch of stuff with that information. Another thing, so like if I'm a retailer and I want to know the number of customers who order a certain product in a week. So the events are customer orders. The number of orders in a week is a Poisson distribution, and then lambda is the expected order number per week. There are Poisson functions in Excel. They work exactly the same way as all the other stuff we've done. Your lambda or your arrival rate is your parameter, and you just plug stuff in. So in the example in the book, they are looking at TV inventory. So they're looking at monthly demand for plasma screen TVs. It follows a Poisson distribution. So you can calculate that out. So if they look at the demand between like 0 and 20, and the mean monthly demand is 17, that's our lambda, you just use the same methodology, but with the Poisson distribution instead of the normal to calculate probabilities. And that's all. That's all I want you to take away from that. The exponential, I don't like, even less to take away. So it's tied to this whole like Poisson distribution. When you're modeling the times between arrivals for customers, that's exponential. So in some of your future courses, you might review queuing theory at a high level, but you probably won't be doing a lot of math. So I'm really going to kind of gloss over this because it's just not that important. So I'm going to move us into our discussion because I really want to get to this, and then I will stay and go through the upcoming assignment for you guys so you can work on that. So our discussion this week was about predictive analytics. I'm going to pause recording for our, let me see. So I'll turn it back on just in case somebody wants to come back to this later. Okay, so for these expected values, you're taking the sum product. Okay, and then for so that's the second part, the average or the expected values. So all it's telling you is like on average, there's 1 to 2 left over, and there's 0 to 1 special orders. Obviously, we can't do a partial order, so that's how I would kind of interpret the averages right there. For part C, they're asking, assume that they make $60 profit on each one they sell, but every time they have to do a special stock out, they lose 20 bucks. So we're going to find the probability distribution of Z, where Z is the sales that they earn. So we're just going to calculate the weekly profit for each of these scenarios. That's all it's asking you to do. So if there's 5 left over and none are special ordered, you need to figure out what that profit calculation will look like, and the probabilities are just copied from, they're the same probabilities. We're just looking at the profit now. So, and I found actually, oh, it's not here, okay. So basically, if you think about it, we're taking the number that we ordered times 60, and then we're subtracting out the $20 for each of the ones that we had to special order. So you can see, like, if we sell all of our air conditioners and don't do a special order, our weekly profit is 300, which makes sense because that's going to be 5 times the $60. After that, we start losing money. Yeah, so okay, yeah, make sure you read that carefully. It's not that they make $60 profit and then lose $20. It's that every time they do the special stock out, they lose $20. they don't make any money. So it's not in their favor to do that. They're trying to avoid having to do those special stockouts. And then once you have this table, your expected weekly profit will be a sum product of the weekly profit and that probability. So 0 times this probability plus 60 times this plus 120 times this, so on and so forth. So if you do that calculation correctly with the sum product formula, you'll get that about expected weekly profit of about $214. Okay, so I just wanted to kind of walk you guys through that at a high level. I don't want to like totally give it away, although maybe I did, but just so you know you're on the right track. You can come back to the recording if you start to kind of get confused. And if you, between the recording, me walking through it, and the textbook, you still get stuck, just send me a note and we'll figure it out together. Okay. Okay. That's all I got. We're like 6 minutes over, so I'm gonna let you guys go. You can drop off. If anyone has any questions, I can stay on for a few minutes.
Thank you.
Thank you. Have a great weekend.
Thank you.
Thanks, bye.
Bye.
So I'm gonna run through it tonight and then tomorrow and kind of go through. I mean, having that there was definitely helpful for me. So just kind of a bounce back between the textbook and here, and I'll even try to Google some things. If I have any issues, I'll definitely let you know. I'm still working on getting the other stuff together. I was
Okay.
just after last night, I was just kind of, my brain was just fried.
Yeah, no problem. And you can see like how much less there is to do this week. So hopefully that like alleviates some of the stress.
Yeah, and I've got that, you know, the template or the first thing about the Excel, and then I looked on like LinkedIn Learning, and then something else.
Oh, I forgot to mention this. I did do something for you. I don't know when it will go into effect,
Okay.
but I have an enterprise account through my institution for DataCamp.
Okay.
Have you heard of it? Okay, so DataCamp is like a really great site that they have like all these courses for a lot of different things. They do like Python and R, like coding, but they also do like they have a couple of intro to spreadsheet courses and basically Excel. And so I submitted a request for them to give me an account for this course so that I can assign a license to you as a student. And so whenever they do that, sometimes it takes like a week. So I don't know when I'll get approval, but as soon as they give me approval, I'll add you as a user, and it'll send you an email and allow you to register. Don't register for DataCamp until you get that email, because it messes people up if they, like, some people got impatient in other courses and created like a personal account. And then it got all messed up. So just wait for the DataCamp invitation.
Okay.
And then it gives you like free access to the courses that I assigned. So they're way better than any other course like LinkedIn Learning, because the way that DataCamp builds their stuff, like their coding and Python, it's like an in-window thing. So you're actually like hands-on going through each exercise in the terminal, if that makes sense.
Yeah, absolutely. It kind of sounds like something I had called Skillsoft, and then I used to do with I think through Pierce County, I found like lynda.com or Lynda.
Yeah.
As well, so.
Yeah, Lynda is now LinkedIn Learning.
Oh, is it? They merged? Oh,
they merged.
Yeah. It was good. They had a lot of, I used to tell a lot of the people that were under me, you know, to get on there to help working out with their different like certifications and stuff like that.
Yeah, I like Lynda a lot. So, but whenever that comes through, I'll just assign you all the spreadsheet courses. And then at your, like, if you just want to go through them on your own leisure, you have them available to you. Otherwise, you know, you'd have to pay for them. But if I can get them to you for free, then you might find those to be really helpful too. So as soon as I get that, I'll let you in. I just don't know how long it'll take them to verify that I'm a professor.
Okay, I understand. Well, thank you so much. I really appreciate it.
Sure. Have a great weekend.
All right, you too. Bye-bye.
Bye.